So let me recall what we did yesterday. We started with the Brauer class and we presented it by a Brauer-Severi variety. And then the first observation was that automatically the pullback of alpha to the Brauer group of the Brauer-Severi variety will be trivial. And so we say alpha is split by the Brauer-Severi variety. That was somewhat the crudest way to split the Brauer class. And then we argued that if any morphism from y to x splits the Brauer class, then necessarily there will be a rational lift of f to x. Or conversely, if morphism or rational from y to p is given, and we define the composition with the projection to x, then its pullback will be trivial. So any such y will split the Brauer class.
If you have a rational map there or not.
Right, but yeah. Well, if you have a rational, then you will only get a rational map here, and then you get something on the function field of y and not on y itself. You have to be a little careful. Okay. So then there were these examples. There were three examples apart from putting back to the Brauer-Severi variety. The first one was there always exists a y just by taking hyperplane sections in P such that this morphism here is finite, or generically finite. Okay, so that was the first example. The second example was exists a relative curve the dimension of y, so the dimension of the fibers is generically 1. Just by taking, one less hyperplane section, and that gives you a relative curve over x. Here, yeah, and then the third example was we take just one hyperplane section, hypersurface section, which is a Calabi-Yau, relative Calabi-Yau in y.
Sorry, could you repeat the context for the x in item 2? It was not for any variety. It was the.
No, I take any Brauer-Severi variety and just take hyperplane section so that generically I get a curve in the fibers.
Oh, really for any? Okay, great. Okay.
I mean, I can always do this, right?
Okay, I see. Thank you.
Do you know if the first example is related to a construction like this? Like you can represent it by a Gm-gerbes, and the Gm-gerbes by pressure digitally as a finite flat cover that can be taken and smoothed. So this finite flat cover of the gerb is a finite flat cover of X to trivialize Y, and I wonder if the first example is related to this.
Yeah. My gut feeling would be yes, but probably not in a direct way. I think you can probably use this one to get a finite flat cover of the new engine if you want. But I'm not sure what the other. So there are certain disadvantages that have to do with these invariants. So this degree here depends on the order of alpha, or the index of alpha. Here, the curve, the genus of the curve depends on the order. So let's say it depends on alpha. Depends on alpha. And here it's the dimension of y that depends on alpha. Okay. So these constructions are nice geometrically and everything, but somehow they're not uniform if you let the alpha vary. And then I explained that there's this question that go back to way back to Roquette and then by Clark and Saltman, asking if alpha is is a Brauer class of any field, so think of the function field of X, does there exist a curve of genus 1 such that the pullback alpha C is trivial. So that is there a curve of genus 1 that splits of genus 1 such that this curve splits C. Okay, so let me give you the easiest examples where this has been checked. So the first example starts with index 3. So this automatically implies that the period of X, so the order of alpha, the period of alpha is 3 as well. And this goes back to Huybrechts. And then it's also recalled in the paper, a nice little paper of 2 pages by Lyon and Leroux. And that goes as follows. Well, I take it's essentially this construction. So if the index is 3, then there exists the Brauer-Severi variety of relative dimension 2. So the fibers are P2s. And then what is a Calabi-Yau on a P2? That's of course a curve of genus 1. So apply construction, apply P, and then get a relative genus 1 curve. How was this constructed? Well, you just take Z of S, where S is a section of the anti-canonical bundle, relative canonical bundle, and then you have to twist it high enough.
But if you're over function field, you don't really need to twist, you just take anti-canonical.
Right. If you're over field already, then you. So that's the case. Index 3. Then they did something similar for index 2. So this, of course, implies that the period is also 2. And in this case, we know. So then alpha is represented by Brauer-Severi variety, and now the fibers are, which is P1 bundle. P1 fibers, P1 bundle. And then, so the relative canonical bundle, the fuel is fiber-wise O2. We don't want to take a section of this one because that gives you just the generically finite member onto X, but you take, consider a section of its square, and then again, you twist high enough, you want it over the righty, and if you're over here, you don't need this twist. And then what you get is this with the zero section will be, will have a relative degree 4. And then you take the double cover of P ramified along these 4 points, and this gives you ramified over Z of S, and that's then a genus 1.
You need K to be even to take the square root of. Take the square root of the platform.
That's not a square root. That's the dual.
No, but like for the construction of taking to one cover, do you need K to be even in the twist so that your class is 2 times something?
Maybe. Okay. Okay. And then the next case, maybe I'll give you this one as well. The index of alpha is 4, and the period could be 2 or 4. Or 4. The interesting case is the index 4 case, and then we represent this Brauer class by a P3 bundle. So that's a P3 bundle. And then the observation is, so you know, if you take 2 sections of O2, so complete intersection of O2 of dimension 1, that will give you a curve of genus 1, right? So observe that O2 plus O2 is isomorphic to say pi lower star O1, 2, where phi is the projection from P1, P3 to P3. Right? I mean, this is the line bundle O1 on P1, tensor the line bundle O2 on P3. If you take the direct image, of course, just get the global sections of O1. So there are two of them, and that gives you this direct sum O2 plus O2. So you want a section, so you want to construct this bundle here on this P3, and then take a section of this one, and then then one argues they exist P prime over X, which is a Brauer-Severi variety dimension 1, representing 2 times alpha in the Brauer group. Okay, and then we globalize this thing here to the relative situation where I take the product, phi product of P prime and P, and just project to P. Okay, and now on the P prime, so on the let's start with P. P is P3 bundle, so we know the relative canonical bundle exists. So what we have here is the O4, relative O4 exists. Right? This is the anticanonical bundle. P prime is a P1 bundle, so there is no, if this is a non-trivial Brauer-Severi variety, there will be no O relative O1, but there will be relative O2, which is the relative anticanonical. So this one here has an O2. Exists. Okay. You cannot simply pull back an O1 and an O2 from here. So this doesn't work naively, but the product still exists. So, but O1, 2 exists on P prime. That's their argument on P prime X, because somehow the obstruction for this O1 to exist is the class, the Brauer class of the Brauer-Severi variety, which is 2 alpha, and then the obstruction class for O2 to exist is it's not alpha but 2 times alpha, and then these two just cancel each other out.
So it's a kind of two twisted sheaves, which becomes
right, exactly. So that's actually quite nice. And then you take a section on P of the direct image of this line bundle, and that the zero set then will be a genus 1 vibration.
Sorry, what's the base thing? This example? I think you're using some vacuum.
Some what?
Some vacuum.
Oh yes. So probably the field, probably the base field K should be infinite or something. No, but typically somehow, I mean, this thing will have sections. I mean, again, I have to twist high enough here. This thing will have sections, and if what you get is worse than the genus 1 curve, then somehow you're even better. Then you get some rational curve in there. That's So then they have a similar construction. Geometrically, it's very similar for index 5. Index of is 5. So again, Young and Poor. And there's something For index this, the results okay for index 6. That's taught by Ashawell. And then there's also some partial results depending on the base period of index 7 by maybe there's some other results I don't know, but somehow it's all for low periods, small periods, small. Okay. I think this is all more or less everything we know. And in the paper, in this little paper by De Jong and Ho, so you can, if you read between the lines, they seem to doubt somehow that there's an affirmative answer for the question that you can find elliptic Jennings curves in Okay, so now the next part is on abelian varieties. And we toss this over. And there is a result by Ho and Leo and Lieblich, which are also by different arguments was proved by Anjou and Coel. And this says the following. So you take any Brauer class. In fact, they work over a field, but let's stay in the geometric field. Then they prove they exist in abelian variety. A over K plus the torso B for A that splits alpha. Let me again say if everything's over one field, then I have the pullback map to the variety B. So if I pull back to the abelian variety, nothing will happen because the abelian variety by definition has an origin. So if the pullback to the abelian variety was 0, I could stay 0 if I restrict to the origin. That means then the original class was trivial over K. So it only makes sense somehow if I'm allowed to put torso here for some abelian variety. And that's the statement that the alpha goes into the trivial Brauer class. The idea is actually to use the curve. So the idea is use complete intersection curve, relative complete intersection curve C in a Brauer-Severi variety, and then for A you take roughly pick 0 of this. Let's do this over field. Okay, you take its Jacobian, and for B you take its Albanese. And then, if you construct the curve like this, then we know the pullback of the Brauer class to C will be trivial, and then you have to argue that's also trivial on the Albanese. And this is what's done in Ho and Lieblich, and Oel and Anjou, they instead use argument by Ho. I mean, there's some work to do here, of course, in order to prove that it's trivial over B, and Anjou and Oel, they use the projection here, and the fact that this is a Brauer-Severi variety, and then somehow so this one, these two are stable birational, and then okay, good. That's this argument. Yeah. Okay, so the remark here is that both the abelian variety and also the torso depend on the class alpha. A and B depend on alpha, and in particular also the dimensions are no control over the dimension of A, the dimension of B. You see, because we didn't have any control over the genus of the curve C, that was just constructed as hyperplane sections, and how many hyperplanes. So and the genus depends on the dimension of P here, and also which power of the relative of one really exists as an eigenvalue and so on. So this is the dimension of those things. It's nothing. It depends heavily on the class alpha and at least on its index.
The projection in QL doesn't have a rational section in general, so you run Brauer-Severi. So from symmetric power to the detached.
What was the question?
Is it a projective bundle or Severi-Brauer?
I think it should be projected bundle, right? Yeah. Okay, and here's the result. It's very similar in style to this one. So this is again going to work with somebody called K, and it says the following. So we give us a projective variety over an algebraically closed field. We let K be its function field. Then exists an abelian variety over K, and for each Brauer class in X, the torsor B alpha for this abelian variety, so everything is over the function field K, such that that splits the class alpha. So here a few words, remarks. The first remark is we don't. Our methods do not allow us to treat Brauer classes for the function field. The Brauer group, let's say if X is locally factorial or smooth, is a subgroup of the Brauer group of the function field, but the Brauer group of the function field is much, much bigger. And we don't have to say anything about Brauer classes, general Brauer classes on the function field. So these Brauer classes we can deal with are called unramified, so can only deal with those. So only for alpha. The second remark is, so it's worth to emphasize, this abelian variety doesn't depend on anything else. So A is independent of alpha. And the same cannot, at least we cannot say, and I wouldn't believe it, the same cannot be said about this, the torsor B alpha, so that probably does depend on alpha, but its dimension, since it's a torsor for the abelian variety A, will be independent of alpha. So this is opposite to, in contrast to the whole Liebig and OL result, where everything, even the depends on alpha. Okay.
Like there's examples where you can see different dimensions in this.
Yes, yeah. There's no, at the end they say, somehow they try to bound the, it's essentially the genus of those curves, and roughly it goes with some power of the order. So there's no way of, just by the very construction, it's constructed, these curves are constructed as complete inflection curves in the Brauer-Severi variety.
Ah, right.
So there's no,
there's not like a best way to do that would preserve the dimension.
Yeah, so as I said, there are two things. First of all, the dimension goes up. That means you have to take more and more hypersurface to get your curve. That makes the genes explode. And also the existence of the relative hypersurfaces. The degree depends on the order,
Right.
because we don't have no one relative O1.
Right.
So there also we have to go to the index of the output. So it's there's no way of doing this. Okay, now the idea is so I give you the idea without giving any details, and then I'll discuss the case of elliptic features where everything is much more concrete, and we can actually improve the results, at least for elliptic features with this section. Okay, and then because there we actually find elliptic curves. Okay, so what's the idea here? The idea we consider a complete family of covering dominant family of smooth curves. So there's a map to some projective space. It's called U. Dominant family of smooth curves. So you just again X is projective. You can from the beginning you can assume X is normal because we're talking only about Brauer classes over the function. So we only split over the function fields. So you can assume X normal. So you find a family like this that complete very ample complete intersection curves in X that cover. Okay. Then we take the relative. So then there's of course the relative X0 of C over U. Okay, so that's a relative X0 over U, and for each alpha on X, we can construct this thing that I denoted X0 or PD alpha of this relative family. Let me recall what this was in terms of Azumaya algebras. We represent alpha by an Azumaya algebra, and then we look at modules on these curves. So the fibers are curves in X, on sheaves on these fibers that are modules over the restriction of the Azumaya algebra. You can also think in terms of alpha twisted sheaves. So if you represent alpha by a check co-cycle, then on each curve you look at alpha invertible sheaves that are twisted with this co-cycle of a certain numerical value. Okay. Or again, if you think in terms of gerbes, you fix a mu-n gerb for alpha, and then you look at moduli space of invertible wave one sheaves on the gerb. So all these, in any case, there is a moduli space that uses either Lieblich, Simpson, Yoshioka, Hofmannstur, and so on. And in any case, so this lives over U. Every object in here, so if one take a curve in here, then what I have here is the family of, we call it like this, alpha twisted invertible sheaves on C. In particular, of a certain degree, which I won't fix, in particular, I can always twist by take the tensor product with any degree zero line bundle on the curve.
So one means like the pullback of alpha to C by alpha here.
Well, I'm really looking at this as a moduli space of sheaves on X.
Oh, right.
So it's really only the restriction of alpha to C level. But I mean, your point comes in a second. Just give me.
Sorry.
I don't. So this is clear. The fiber is clear. Torus under peak zero. I can just twist everything by line bundle of degree zero, an honest line bundle of degree zero. So this thing here is a peak zero torso. So relative over U. So we think of this thing as a moduli space, or as an open subset. Think of this big D alpha as an open subset of a moduli space of twisted sheaves on X. Okay. Now let's assume this moduli space is fine. Okay. So that means there exists a universal bundle or sheaf, bundle P on. So always the universal sheaf sits on the product, it lives on the product of the moduli space times the variety. And here, since everything is relative over U, this thing lives on the fiber product of the varieties, or the family of curves times the moduli space over base U. Okay. So there's universal bundle, but by definition this is a moduli space of twisted sheaves. So this thing is twisted by the Brauer class, twisted with respect to the pullback of alpha. Okay. Now, this is the twisted Poincare bundle. If you have a twisted line bundle then the Brauer class of the twist has to be trivial. Hence, under the projection, so under, I have now one projections, big D alpha CU, phi product over U with a family C, then first project to C, and then to X, and if I call this pi, the pullback of pi, of alpha under pi is trivial. Okay. And now this thing here, this thing is a torsor, so these things over U were a torsor for big 0. So this is a torsor for big 0, C U, and then base changed to C. Okay. And the generic fiber of this gives us gives us some abelian variety. It's an abelian variety over the function field of the family of curves. Okay. So that's not quite what we want, because we want an abelian variety in a torsor for it over the function field of X. But now you just restrict the whole family to a subfamily of curves that is for which there's only one curve going through the generic curve. So I restrict. So what we get here is now restrict to a subfamily such that the projection now is generically injected. So and then if there's a universal family for this family, then of course the universal family still exists when I restrict to the subfamily C0, and that means the pullback of alpha to C0, the same argument is trivial, and if this is birational morphism, then I'm sorry, alpha 0, you first restrict to alpha 0 and then pull say this one, then we get, I should say this, and then I get the restriction of this thing, C0, U0, C0, that's a torsor for big 0, the relative big 0 of the family. And this is now the generic fiber. Here's our abelian variety. It's an abelian variety over the function field of K0, of C0, but this is the same as the function field of X.
I'm sorry, would you be able to take 5 seconds to repeat what this pic D alpha, what this relative pic zero torsor, what it means to have this alpha twist? I'm confused. You said if it's a lot, yeah, I'm just confused what this object
Let's
is.
do it again. So I represent alpha by an Azumaya algebra.
Yes.
Okay, and then
On X, we're on X for this time.
sorry?
On X.
On X. That's on X. That's on X. And then the fiber of pic D alpha C U over U.
Yes.
Over C, and then over the fiber over C is the set of all A C modules. So I restrict the Azumaya algebra to C, and I take the modules of. So these are line bundles, but now A is not O. So the line bundles here correspond to the rank of A and square root.
I see. I shouldn't think of it as like, it's not like twisted sheaves on C. It's something a little more.
It is. So if you think of this Azumaya algebra, so this Azumaya algebra will give you mu n-gerb, and you think of this as line bundles on this mu n-gerb over the curve C.
Okay.
So the unusual thing is here that like if this is a smooth curve, we know the Brauer group is trivial, so you don't expect some of any
Right, the twists don't mean much.
right. The twist there don't mean much, but if you so maybe it helps someone to look at the generic curve. If you look at scheme the generic curve here, then that's a curve over some field, and that has a Brauer group.
Right. Oh, because it's a non-closed function field.
Right.
Ah, I see. Okay. This is okay. I'll think more on this. Thank you. That was very helpful.
Okay, so this is roughly the idea, and now maybe it becomes all a bit more explicit when I talk about.
Sorry, can I follow? Because I'm still confused. That if does it mean that pk is actually asymptotic to the untwisted one, like because
Well, once you fix the thing there, then it becomes you can trivialize it.
Yeah.
And there's no distinguished choice for the E. So that's why it's only a torso over pic zero. And not isomorphic, not naturally isomorphic to pic zero. For each individual curve, of course, you could say, well, just pick one and make it isomorphic. But if you do this in the family, then you cannot. That's the whole some of the magic of the construction.
Okay, I see.
Thank you. Yeah.
Okay. Elliptic KPs. Elliptic KPs. So I start with an elliptic KP over P1, and really elliptic in the sense that they also exist in section. And then the proposition here, some of the result gets a bit better. We can actually answer this question by Clark and Tolman. They exist. So this here is what so the function field here is a generic point, and the function field is of course a pure transcendental extension of the base field K. So they exist in abelian. They exist in elliptic curve E over KT, such that for all alpha in the Brauer group of S0, there exists the torsor the B alpha over for this elliptic curve C. So everything is over KT. Everything takes place down here. And now we pull it back to the function field of S0 such that under, when I take C alpha, take here the final product to base change to the function field of S0, so this is over like A0. Then this thing here, alpha becomes triple, alpha splits. Okay, and this is of course, this is the genus 1 curve, this is a torso over the elliptic curve E base change to the base field, to the function field of S0. Okay. So in a way, so this answers this question by Clark and Sorben, but actually gives something stronger. Namely, not only do we split every at least unramified Brauer class, but we split it over by a torso over the one fixed elliptic curve. Okay.
Does your construction give a homomorphism from the Brauer group to the measure of the Lie group of the varieties? Is it a homomorphism or just
In the general case?
in the general case?
And you want, so I do have this morphism Brauer next. And you want?
To the measure of the Lie group of A. From Brauer.
Yes, I think it does. By the very construction. So these, you see in these, this is the question whether if I take two different alphas here, whether the peak for the product is actually corresponds to the torsos that's the product given by the product of the two torsos. And that's right, because if I have two twisted sheaves on the fibers, one twisted by alpha 1 and the other one by alpha 2, the tensor product will be twisted by alpha 1 times alpha 2. So I do actually get.
So you can compare period and index on both sides? Period.
Yeah, but I'm afraid it's getting complicated. Yes, so I'm not. I mean, we discussed it, but I don't think there's a. Yes, definitely can, but I'm not sure there's a good answer. Okay, so what's the idea here? So maybe it becomes more explicit in this case. So the idea here is, so the Brauer class in S0, so we are on an elliptic K3 surface with a section, so I can identify this with the Tate-Chavez group of S0 over P1. And then this alpha corresponds to Tate-Chavez twist of which I put as alpha. So that's the Tate-Chavez twist. In particular, its relative peak 0, so compactified, is the original S0. Okay. And so this, you can interpret this as a moduli space. So this is a K3 surface. You can interpret this as a moduli space of sheaves on the K3 surface. This moduli space will not be fine. That's only a coarse moduli space. On S0, and in fact, the obstruction. So the obstruction for universal family to exist is always a Brauer class, and it's exactly this Brauer class alpha. The obstruction class is alpha. Or in other words, there exists the universal sheaf P on the moduli space on the original surface. So now the original surface is S, and the moduli space is S0. But it's twisted. So the S0 is a moduli space on S, and it's twisted. So there's an obstruction class on the moduli space, and this universal sheaf only exists as a sheaf twisted by the obstruction class, twisted with respect to 1 alpha. And of course, then you check it actually lives over over the fiber product. And that's exactly what we needed. Now I project to S0 as before, and so the obstruction class pulled back has to be treated as a Brauer class up here, and since there exists rank 1 twisted sheaf, it has to be the trivial Brauer class. And then the final point, somehow to match it up with the general idea, is if you have this universal family, now you can view this as so by the constructions, S0 was the pick 0 of S, so that was a moduli space of S. But now you can use this universal family to view the S as a moduli space of sheaves on S0. You restrict this thing to a point in S. What you get is not a sheaf, but a twisted sheaf. And so this S is actually some pick D of alpha. Pick D alpha of S0 over P1. And that fits with the description before, and so you actually get a torso over S0 itself, which is pick 0 of S0.
So this E is just a generic fiber of the original.
Exactly. Yeah. So the E is then generic fiber of S0. So the next question would be, what happens if your elliptic K3 doesn't have a section? Can you still prove the same thing? And the answer is no. No. But can a little bit. So this was the position. If I so this still holds here. Still okay for elliptic K3 surface without a section. But then we can only say something for Brauer classes whose order is prime to some integer. So for alpha, the order of alpha is prime to some integer. So instead of explaining this in detail, I'll give you another result that deals with arbitrary K3 surfaces. So of course, the very general K3 surface will not have an elliptic curvature, but at least of a complex number, every K3 surface has a family of singular elliptic curves. Okay? So you could think, so can I use the family of singular elliptic curves to do something similar? And in fact, you can. And the proposition we can prove is. I didn't put this. This is of course also joint work with Dominique. And says the following: so if I have any K3 surface, and just assume it's
sorry, is lowercase k and this elliptic K3, there was no assumption on algebraic closure?
No, algebraic close. Little k is algebraic close.
Oh, little k. Of course, the function field. Okay.
Yeah.
Thank you.
So here I work over C to make sure that there is a family of singular elliptic curves on S. And then I say there exists an M such that plus the finite extension of the function field of S plus an elliptic curve over K such that for all alpha in the Brauer group of S, with the property that its order is co-prime to M, there exists a torsor T alpha, and a torsor for E, everything over this finite extension, such that alpha, that this T alpha splits. So I can first restrict to the function field, and then I go to the finite extension of the function field, and from here I go to this torsor, and this thing here maps alpha 1. Okay. So there is this finite extension here, which we can't get rid of by our method. But once you're willing to pass to a finite extension that works for all the Brauer classes, then you have the same statement as before. You can split every Brauer class at least of order co-prime to M. And the degree of this extension, this has to do with if we know that every K3 surface has a family of elliptic curves, but typically these families have the property that through the generic point in X, there's more than one elliptic curve going through. And the number of elliptic curves that go through a generic point, that's exactly the degree of this split extension. Well, then I had planned a whole section on the special Brauer group, but I think I just thank you.